Okay, thank you all for coming to our Monday afternoon seminar. Our speaker today is our new attraction de talento fellow, Matteo, and he will tell us about probing inflation with primordial messengers. Please, Matteo.
Thanks. It's great to give a talk. It would be nicer to see you all in person, but this is the best we can do at this time. So let me just start. And well, today I would like to talk about inflation, and in particular, what sort of messengers, what sort of signatures we should be looking for in order to test inflation. Let me just stress, please feel free to interrupt me at any time. I actually like that, and we can turn it more into a discussion. Otherwise, I just go ahead. So let me give you a brief. Okay, so this is not working. This is working. Yeah, perfect. Let me give you a brief outline of the talk. And it's going to be very simple. I just start by talking about single phase role inflation. This is the most popular scenario, certainly the most well-studied one. And I'll try and make the case as to why we ought to go, we really must go beyond it. To convince you of that, I'll first focus on a very specific example, a very specific class of inflationary models, and on top of that, a very specific observable. And then I'll try to generalize that to give you a much wider perspective. And this is, perspective about the inflationary particle content. These days, this is called actually cosmological collider physics, but it's pretty much the same idea. So if you heard it as that, you will recognize a lot of the same feature. Now, inflation. So what's inflation? I guess with this audience, I don't need to say much more, but let me just very quickly, very briefly remind you of things you already know. We want to accelerate the universe. Normally, we would write down the Friedmann equation. On the left-hand side, we've got 3mp squared h squared. On the right-hand side, we've got the universe makeup. And remember, you cannot accelerate the universe with just matter or with just radiation. You need something else. Well, normally, you would put, say, a cosmological constant in there. But of course, if you put it in the very early universe, then you will accelerate forever. So that's not what we want. We want something that looks like a cosmological constant for a while. And then it stops dominating the energy budget of the universe. And that's exactly what you get, perhaps with the second simplest idea that anybody would come up with. Not a cosmological constant, well, what's the next best? Just a scalar field with a potential that looks flat enough. And that's what we have here. And that's what's called slow roll inflation. So we've got this inflaton field, which is rolling down this potential very, very slowly because the potential is very, very flat because it needs to look like a cosmological constant. But after a while, when it goes down this potential, its kinetic energy dominates or is comparable with the potential energy, and that's when inflation ends. And so in one single go, you have something that accelerates the universe, but it also stops accelerating at the right time. And that's what slow-roll inflation really is. This is the main idea, okay? And just a couple of slightly more qualitative things about single-phase slow-roll inflation. I've already stressed that your potential needs to look like a cosmological constant, so it needs to be flat. Can we quantify that a little better? Well, yes. Pictorially, what do you want? The inflaton potential to be flat, so v prime over v needs to be small. You put the appropriate dimensions in front of it, you end up with quantity like mp squared v prime over v squared. Another way to write it down is h dot. H is the Hubble rate over h squared, and that's the way you introduce the first slow-roll parameter, usually called epsilon. If you want inflation, you need that to be small. Okay, so that's slow-roll inflation for you. Now, that's the potential being flat. If you want it to stay flat, essentially you want the time variation of this epsilon to stay small for a while. And that's what the second slow-roll parameter, eta, is all about. And some of you will have a different definition in mind for eta, which is directly connected with the inflaton mass, but the two, of course, are going to be related. Now, I stress about inflation being flat for long enough. Let me remind you that we need at least 50 or 60 efforts of inflation for the CMB observation to be explained. Otherwise, when we look at the sky, when we look at the CMB at different angles, we see that essentially the temperature of the CMB is pretty much uniform up to 10⁻⁵ correction. That fact cannot easily be explained unless there is a common early epoch of accelerating expansion, and that's why inflation does a good job. And actually, the simplest ideas of how the inflation might have taken place in scalar field, slowly rolling, actually works out pretty well, as we will see. Now, that's what we've talked about so far, this accelerating solution, everything that I wrote down so far was a background level. But then, of course, we know that if we have the background, if we get the background to work, we would immediately want to consider fluctuations around this background. So you've got your FRW background working out very, very well. But now remember that this is GR plus a scalar field. So there are the usual degrees of freedom, 2 tensor plus 1 scalar, and you expect fluctuations around that. And well, typically, the way you represent that, you write down the quasi-de-Sitter, the FRW background. The fluctuations are typically zeta. They're denoted as zeta for the scalar ones and gamma for the tensor perturbations, which are essentially gravitational waves, as we'll see, primordial gravitational waves, I should say. Now, okay, so we've got these fluctuations, scalars and tensors. If you want to study them, I guess the first thing you do is you start writing down endpoint functions of these observable. The easiest one is, of course, the power spectrum. If you calculate the power spectrum in single phase Roll inflation, the result that you get is this one right in front of you now. And this is, very easy to figure out expression. Remember, this h squared over epsilon is the only thing you don't know. And so should you know this number, as we do from CMB observation, that's roughly 2 times 10 to the minus 9, then really you know the ratio between h squared and epsilon. And that's quite a lot because, well, epsilon is the Roll parameter and h is the Hubble rate. You can think of it roughly, in the inflationary context, we think of it roughly as the energy scale of inflation, okay? So this is stuff that we know. And so it's a h squared over epsilon is a number that we know. Now, on top of that, there is the k dependence, right? How does this power spectrum depend on the scale? There's a very slight dependence here. You can see that this ns minus 1 is proportional to minus 2 epsilon minus eta in slow roll. This is, remember, ns is 0.96, etc. And that's a very, very small number. That's why we say that the scalar power spectrum in single phase roll inflation is slightly right tilted, okay? And now that's for the scalar case. Of course, you will ask, how about the tensor case? Well, we can write down the 2-point function in single phase roll. We get an even simpler expression. It just depends on h squared, really. Now, except the problem is that we don't have a number for this. We don't have a number for this because primordial gravitational waves have not yet been detected. So the only thing we have is an upper bound on p gamma, on tensor fluctuations. We also know that the tilt, this nt, is actually also small and also typically red. So again, it's going down as a function of k very, very, very slowly. People don't directly talk about p gamma. They talk about p gamma over p zeta, which is known as the tensor to scalar ratio. And I believe the best bound on that still is the one from Planck, which is 0.056. But there's reasons to be happy because in the future, very near future, actually, CMBS3 will take it down to hopefully 0.01. And CMBS4, and I should also mention LIGHTBIRD, the Japanese mission at CMB again, which is going to take it down to also 10 to the minus 3. It's comparable to CMBS4, okay? So this is what we expect, what we know for single phase Roll inflation. And let me just give you a little picture of why these thresholds that I mentioned that we're going to cross are important. Let me just go back. Remember, we're going to get to R roughly 10 to the minus 3 with CMBS4 or LIGHTBIRD. Why do we care? Why is this not just a, let's say, quantitative improvement? It's going to be a qualitative improvement. Now, one way to look at it is very naive, but I like it anyway. So let me just bug you with it. Remember, ns minus 1 is roughly equal to minus 2 epsilon minus eta. Now, if you don't know anything about the specific inflationary model and you decide to go for epsilon of order eta, then everything is fixed and your R is going to be of order 10 minus 2, which means we're going to see something soon, maybe with CMBS3. Now, if that's too naive for your taste, let me remind you a very nice model, nice in the sense that it perfectly agrees very well with observations. It's relatively easy to embed it, let's say, within supergravity or even string theory. And this model has very specific predictions. It's the Starobisky model or R-square model. What we get for it is that 1 minus ns is 2 over n is the number of efforts. So you fix that because you know ns, and then you got R for you ready. You just put in the number, you got R is over the 10 to the minus 3 or slightly larger. That means that at least the standard Biskey model, which is doing spectacularly well when it comes to observation, is going to be ruled out or hopefully ruled in by observations. So some observations are coming, and they are crucial. They are actually qualitative thresholds, not just a little bit better than what we were doing before. Okay. With that said, let me just conclude this part about single field role inflation, just the overall status of the field, by showing this very famous plot. You probably all know on the y-axis, there is the tensor to scalar ratio. It can go all the way to 0. On the x-axis, we've got this ns, and remember, it was 0.96 something, the value that Planck finds. You see a lot of dots, some going up, some going down. This is the whole story of alpha attractors, but what I want to stress here is that several single field slow roll models are doing extremely well. Standard Biskey inflation is the one sitting at the very bottom here, the one that looks the best, and that's also known as R-squared inflation. And so overall, just by looking at this table, you would say single field slow roll seems to be doing very well. Why are you giving this talk? Why are you bugging us? Let us go home. All right. Well, there are reasons, and let me just try to list them to go beyond this scenario. And the first one is actually very practical, if anything else. Now, remember that when I wrote down the tensor power spectrum, really it was just a function of h. And so if we detect primordial gravitational waves, the second we do that, you will be tempted to say, oh, we know h, we know the energy scale of inflation, so every single inflationary observable will be a fantastic portal to that energy scale. Well, now most likely, remember, this energy scale can be 10 to the 13, 10 to the 14 GeV even, so you can do particle physics with it. Fantastic, let's be very excited. But that's true, but one needs to be careful because this expression is correct only in single field roll inflation. So if we want to have, it's going to be an extraordinary claim to say that we have primordial gravitational waves, then we need extraordinary evidence, and we need to figure out if that's the energy scale of inflation. So that's why we should figure out what else can happen and be able to characterize it, rule it in, or rule it out. And I say this, and let me move on to the second reason, because even in top-down approaches, let's say in string theory, the most natural thing to expect, now remember the whole story, you probably know more about this than I do, 10 space-time dimensions, you need to compactify 6 of those. In the process of doing that and reducing yourself to a 4D low-energy effective field theory, you typically end up with many moduli fields. Now, moduli fields, as far as I know, are scalar fields, but there's plenty of room within this construction also for gauge fields, even for Kaluza-Klein modes, etc. So the presence of many fields acting during inflation is perhaps the most natural scenario from the top-down perspective. So we must be ready to test and characterize multi-field inflation as well. I mean, if this is the most likely scenario, we better study it. Now, on top of that, moving on to reason number 3, from the point, if you're just interested in signatures, that's even better because the signatures associated to extra fields are plenty, and actually really, in several cases, they're actually really easy to test with upcoming observables. Now, if you even focus on just extra field content that you want to test only on the gravitational wave side of things, which you don't need to, but just to give you an idea, then there's plenty that you can test for example, the power spectrum scale dependence, its chirality, its non-Gaussianities. And just by looking at this, you will learn quite a lot about the inflationary particle content. In some cases, just a couple of information will immediately rule out single field slow roll inflation. So I hope I've convinced you that this is important. Now, in order to make the case more precise and hopefully stronger, let me just focus on one specific example, which is the axion inflation class of models. This is not going to be just about one model, it's a whole class, okay? And I want to restrict myself to primordial gravitational waves. Now, I don't need to, and at some point I will actually add a few more physics to this, but just to show you the power of one single probe at several scales to test inflation. So I hope I can make this case for you. So let's talk about axion inflation. And in the next maybe 3 or 4 slides, I'm going to take some sort of historical perspective. I'm going to introduce very quickly several models that have been called during the years axion inflation, in this case natural inflation. And we'll go all the way to the models that these days are more studied for several reasons. And so please feel free to ask any question about this. Now, this is the model that is very, very well known. It's put forward by Fries, Freeman, and Lynch a long time ago. And it's just GR plus the scalar field as always. You've got this d phi squared, the kinetic term, and the action-like potential. I remember this field as a remnant of shift symmetry, as you would see in the cosine potential. In fact, this potential was written down because you can think of it as the result of non-perturbative corrections to the potential. Now, normally at tree level, the potential is actually completely flat. Okay, it's a very simple potential, but it's very well liked because the shift symmetry makes it technically natural. Remember, having a shift symmetry means that you have very small corrections to the inflaton mass. You want that because if the inflaton mass is unnaturally is large or is in order Hubble, then inflation will not last long enough to solve the problem that it was invented for. So it wouldn't explain CMB observations. We need the inflaton mass to be naturally small. Okay. Now this model is viable for the axion decay constant f of order m Planck. Now you might be okay with it, and in which case you should be considering this model directly. It is a little bit in tension with data, but what's been done recently and not so recently also is actually opt to look for an axial decay constant which is not of order m Planck, and for a few reasons which I might mention. So one is that at that scale, one expects all global symmetries to be broken, and for you're not so comfortable with shift symmetry at those scales. But in a much more practical sense, all string theory construction that we know of really automatically opt for f smaller than m Planck. So if you believe that any indication should be taken from what's a top-down approach, if all the constructions do have f clearly smaller than m Planck, then you better come up with something at lower energies that does have f smaller than m Planck, and that's not natural inflation by itself. Now, one idea as to how to do this is actually, again, very simple. You just take natural inflation, exactly the same thing I've written down before, and you couple it to something else, okay? This something else, in this case, are gauge fields. Now, let me go one step back and remind you here that if you take the axion decay constant f, and look at the right-hand side of this slide, if you take f to be very, very small in some units, then, okay, your potential is not very flat. If you take f to be rather large, then your potential becomes flatter and flatter. That's what you need to have something like single phase for roll inflation. That's why if you're dealing with natural inflation, you end up requiring that f is larger than m Planck. Okay, that's quite simple, okay? So you want your potential to be flat. Now in this case, as it turns out, you don't need the potential to be, well, you need the effective potential for the inflaton or the axion-like particle, which is the same thing, to be flat. But one way to do it is to convert a lot of the would-be kinetic energy of the axion inflaton into another sector, to give it to another sector, to share it with another sector. Now this sector is the gauge sector. So we've got this minus 1/4 f squared, the kinetic term, and then we've got this ff tilde, Chern-Simons type coupling. Now, because of this coupling, effectively, the inflaton potential is actually flatter. The more you couple it to gauge field, so the larger lambda is, if you will, this coupling constant, which is deciding how large the coupling is, the flatter the effective potential for the inflaton is. So this is an interesting way for you to be able to lower the value of f, much smaller than Planck, and as a byproduct, and this is actually a byproduct, people were not concerned with what happens on the gravitational wave side of things. We're just worried about the sub-Planckian axion decay constant, but as a byproduct, you get a very interesting gravitational wave signatures. Now, this is progress if you're after a sub-Planckian f, but I should say that, again, this is also, this sort of models is also in tension with data, not as much as the natural inflation, but a little bit in tension. And the reason is that if you are able to essentially flatten the inflaton effective potential, and you are as you increase lambda, what happens is that the gravitational wave side of things becomes very interesting. You do produce a lot of gravitational waves with specific signatures. And as it turns out, the amount of coupling that you need to really flatten the potential for you to have the, wait, are there any, I see that are there questions? I should, perhaps I should, give me just 1 second. If there are questions, please ask. I see that there are numbers. Savas, maybe I should ask you, I see that the number is going up of...
Yes, so there is a message by Pierre. He's asking...
yes, please.
If you still have F in the action potential U.
If I still have... So the action potential is... yeah, let me just go back. The action potential is identical as before. So it's this one. F is indeed... Pierre, yes. F, the action decay constant, is still there. But in this configuration here, I don't need it to be so large. I don't need it to be en Planck. I can have it much smaller, so long as I have this lambda coupling here sufficiently large. Everything works out. I do get the proper ns-1. So the potential is sufficiently flat, but there is a very high price to pay. And this price to pay is that I overproduce, or I almost overproduce, gravitational waves. So this model too, although does much better when it comes to data and is able to implement F strongly sub-Planckian, I mean at least 1 or 2 orders of magnitude smaller than in Planck, it still doesn't do the job completely. But if you want to do the job completely, you can do so. And this is one example on how you do it. And so we put forward this model, but also Bart and Soda were working on something quite similar. So we both did. One way to do it is the following. You keep exactly the same field content as before, except that you add an extra field, a scalar field, and you ask that it be the inflaton. So that means that in terms of an S-1, the scalar spectra index that knows about the slope of the potential, well, that's taken care of by the green part of this Lagrangian, which you don't even need to specify, just a generic inflaton potential that we know does the job. But everything that's interesting from the point of view of gravitational wave phenomenology stays the same, because everything that's interesting is on this blue and orange side of the Lagrangian. But what you realize is that F can be much smaller than a Planck, just as before, and you are observationally viable. You're paying a price. The price is that you're adding an extra degree of freedom, which normally you would try to minimize, right? There's already plenty in the chromonatural inflation action. We're adding another one. So this is a price that we are paying, and there's no denying that. But if you do so, then the model is viable. And from the gravitational wave side of things, there are interesting features. So let me talk about that. Now, okay, very quickly, reminding you things that you already know. We are in FRW. We want to consider fluctuations. Forget the scalars for a second. We want to consider just tensor fluctuations. So that's gamma in this equation, this first equation. We've got 2 polarization states. So, well, that's the condition for 2 polarization states. If we write down the equation of motion for gravitational waves, this is the way it normally looks like. A couple of things I want to remind you of. If we were doing single phase or Roll inflation, then the right-hand side here, the source term, would also be non-zero. You would typically get no linear contribution from the scalars, but this is negligible. So you can just solve the homogeneous equation at the bottom of this slide, write down the result, and that's what I've written down for P gamma early on when we started. Okay, that's what you will get. Now, in this case, because you have extra field content, the right-hand side is bound to be more interesting. In fact, the right-hand side will have plenty of contributions for primordial gravitational waves. Let me write it down here. Now, again, I'm writing down this Lagrangian. I have to specify to you the fact that for gauge fields, for this specific example, I'm taking SU2 gauge fields. So you should imagine an index A, a gauge index A in front of F. So this is FA, F theta A, for example. The background values are known, and you can consider fluctuations. And because this is an SU2 model, the fluctuations actually have tensor degrees of freedom in them. So because of this gauge sector, there are tens of degrees of freedom in the gauge sector, and they source gravitational waves directly. In fact, I've written down here the gravitational wave equation of motion. They're going to get plenty of contributions, as I said, also from scalars. So they're going to get contributions from the inflaton part, the green part itself of the Lagrangian, from the action-like particle, the orange part, but also from the gauge sector. In fact, most importantly, from the gauge sector. And I say most importantly, because if you get contributions from scalars, that's going to be nonlinear, right? You essentially get loop contributions. But if you get contribution directly from tensors, this can be at tree level. And if it's at tree level, then it can give you the leading contribution, or at least a contribution as large as the vacuum contribution. And by vacuum, what we mean here is the solution to the homogeneous equation. So now, in these sort of models, because of this extra field content, you get to source gravitational waves and give to them a contribution at least as large as the vacuum contribution. And that's the interesting in this model. There are specific properties of these contributions which I want to talk to you about very, very quickly. Here I'm writing down the equation of motion, metric, tensor, and tensors in the gauge sector. You might be more familiar for the first equation with the variable h, but this is related to h, so you can think of h. X is k tau. Again, you might be more comfortable with tau, but roughly speaking, that's the same thing. But what you see in equation 1 and equation 2 is that, well, the metric is being sourced by the gauge tensors and vice versa. As it turns out, in the second equation, the right-hand side, you can throw it away. It doesn't give you a great contribution. So you can solve the equation of motion for the gauge sector, and then you know it sources gravitational waves. I want to draw your attention to a couple of things. The first one is that in the gauge equation of motion, between the third and the fourth term, there is a minus plus sign there, and that's not a mistake, it's not a typo. The minus plus sign there, or plus minus sign there, is reminding you that depending on the polarization that we are going to be solving for, we get a different equation of motion and therefore a different solution. That means that the right-handed t, or as opposed to the left-handed t, is going to be slightly different. And this is important because given that they source gravitational waves directly at tree level, that means that if the source contribution is the leading one, well, then h left is going to be different from h right. And so we're going to have chiral gravitational waves. And this is important in this model. It's one of the signatures. And of course, you already know that this is coming from the Chern-Simons type coupling because that's the one that breaks parity essentially. Now, one more thing I want to stress is that this equation of motion for t, a lot of pieces in this equation of motion are proportional to psi. And this psi variable is interesting because it's the one that regulates the coupling with ff tilde. I remember ff tilde is again the Chern-Simons type coupling. So psi is proportional to lambda chi dot over 2f. So the bigger lambda is, the more effect you get, the more the right-handed polarization, say, is enhanced with respect to the left-handed polarization. And so the more chiral your gravitational waves will be. Now, what I'm plotting here is just the solution, the wave function for the metric and for the gauge tensors. If you look at the gauge side of things, you can see that as let's start from the very right, from x very large, that means that we start inside the horizon for the solution. And remember, the horizon is at x equal to 1. So if you start from large x and we go towards x equal to 1, we see that actually there is a bump, there is an enhancement in the gauge sector. For them, in this case, left-handed gauge, that's what we're plotting, and the right-handed is actually standard, there's no bump. And with a little bit of delay, with a little bit of lag, there is a bump in the metric field because this is coupled to the gauge field. Now, the result of this coupling, again, is that the metric, the left-handed polarized gravitational waves, are actually enhanced with respect to the right-handed by this little contribution that's coming from the gauge sector. So you can see it already at the level of the wave function. And so let me stop here just a second to say that if there are questions, Savas, please let me know because I cannot see anything on this side. I'll just continue to assume that there aren't, but if there aren't, please yell at me. Okay, so this is the status with as far as solving the equations of motion goes. Before I talk to you about the effect that this specific solution has, the visible effect of this specific solution to the gravitational wave equation of motion in these sort of models, I want to remind you of what's normal, or what's expected if you're playing with single Pfister rho, okay? Now here, instead of plotting the power spectrum of gravitational waves, I'm plotting their energy density, but pretty much omega GW is proportional to the power spectrum, so the behavior as a function of k or as a function of frequency is roughly the same. And in fact, in this black line here, you will recognize the usual behavior. You see something that it's slightly red tilted, so it's going slightly down as a function of the frequency, up to very large frequencies that you see are even above LIGO. That depends on the duration of inflation. Okay. Now this is the usual behavior, and this black line is obviously below my horrible way of picturing the sensitivity of LISA and the sensitivity of LIGO. You can see it's actually quite different, and it's below it. So that's why we certainly cannot expect, we have no right to expect that the single Pfister rho inflation, the gravitational waves coming from single Pfister rho inflation will be, for example, detected at small scales. That's not possible, right? And the prediction says that this is not going to happen. So what happens if you do pictorially actually observe something rather different, such as this one? Well, this is pictorial, right? And we'll get more precise later, but in models of axial inflation, you can get something which is known as a blue spectrum. So something that goes up slightly as a function of f, or things like this one that with this horrible picture that I've drawn, this is a bump, right? It's a bump-like feature in the power spectrum for gravitational waves or in the energy density for gravitational waves. Now, because of this bump, that can be actually very different scales, it is possible to observe primordial gravitational waves at small scales. It's possible to do it with LISA. If this bump were a little bit on the left, perhaps we should be talking about PTA, so for some timing arrays as opposed to LISA. But what this model does is that it stresses for you that we can use laser interferometers such as LISA to actually test primordial physics, primordial gravitational waves. And in fact, let me just stress the second bit, right? The first bit is the non-trivial scale dependence. And when people say non-trivial scale dependence, so this is the trivial one. And in these models, you get something like this, which is non-trivial, okay? Now, the other properties that we have already talked about is the chirality. So let me be slightly quicker here. If I write down the equation of motion for the tensor degrees of freedom in the gauge sector, and those people are going to source a tree-level, a linear level gravitational waves. If I write down the equation of motion for this tensor degrees of freedom, I'm going to get a different equation of motion for the left polarization, the right polarization. Because they're coupled to gravitational wave, gamma left is going to be different from gamma right. Therefore, P left is going to be different from P right. And that's what's known as a chiral spectrum. How do we test a chiral spectrum? Well, when it comes to, it depends on the scale. At CMB scales, for example, we know that in single Pfister rho inflation, at least a low multiple, a low L, if we consider B modes cross-correlated with temperature and isotropies, we're going to get 0. Same thing if we consider EB correlations. But in a model such as this one with this Chern-Simons type coupling that exhibits directly a chiral primordial gravitational wave spectrum, then BT is different from EB, but they're both different from 0. And this is the key. We can test them. Now, this is known. In fact, we pointed out this, we studied a couple of models that have this property, and people took it pretty seriously, and they actually showed, first of all, investigated and then showed that this is indeed testable. For example, with Lightbird. I remember Lightbird is this Japanese satellite that would take care of the CMB, observe things at CMB scales. I remember this is the very same one that will take R down to 10⁻³ comparable to what CMBS4 can do. So what you see here is the plot of TB correlations. Different colors are different regions of the parameter space of the model that I've just talked about. And this model, instead of just writing down the exact features of the model, Thorne, Komatsu, and collaborators, they decided actually to parameterize it. So let me spend a few seconds on how you parameterize it. well, in front of this P source, you put R star, just to give you an idea of how far you can go with primordial gravitational waves. Remember, R is bound, for example, TMP scale, so we need to be careful with that. P zeta is the usual scalar power spectrum. And then there is this dependence on K over Kp. Kp is the pivot scale. And in this sort of axial inflation model, you can put Kp can vary very widely. Okay, we can go from CMB scales all the way to laser interferometer scales. So you've got plenty of freedom there. You don't have a lot of freedom in sigma. For the models that I'm familiar with, sigma is of order 1 to order 10, but not much more than that and not much less than that. Otherwise, your parameter space doesn't really, for example, you don't get a signal which is just as big as the vacuum fluctuations or even slightly larger. For sigma, but in other intervals, you don't get what you want. So this must be clear. So the standard is on anything above the black line there, which is there to show you what instrument noise you might have. Anything above that, you can test this model. But the not so good news is that, well, this model is testable, but the signal to noise ratio for TB or EB that you would get at CMB scales with light, but it's very small. You can see the signal to noise ratio between 1 and 2, it's there, but it's not amazing. This nevertheless was done and was studied. And what they also pointed out is that actually, if you can in this model, move the pivot scales at much larger K, much larger frequencies, then with something which is planned, but it's not there yet, of course, like the Big Bang observer, then you can test the signal to noise ratio actually of the V parameter, this signal to noise of V. Remember on the y-axis here, that's the stock parameter associated to circular polarization. You can test that with the signal to noise ratio of order 5 or 4. So you can do much better than that. But we're talking about BBO, okay? So that's very futuristic. Now, something else that you can do, and I would like to stress here, is that you can test chirality actually with interferometers, laser interferometers, which is also interesting. Now, let me remind you of something that's important. If you want to test whether your gravitational waves are chiral, you cannot just rely on one interferometer, which is planar. And by planar, I really mean just on a plane. You can put it all in a plane. I think most of them are, in fact. You cannot get, essentially because you cannot distinguish, let's say, a left polarized wave coming in your plane from the bottom from a right-handed one coming from the top. That's essentially the situation. But although you cannot do it with a single earthbound interferometer, you can do by considering different cross correlations between interferometers at different locations. And that's because, well, the Earth is not flat. And so you get something which is not planar. And the other possibility, which is actually very interesting, I learned about it recently, is that even LISA, although you might think, well, that's a planar geometry itself, so what are you talking about? Well, the fact that actually with respect to the cosmic frame, that's the one with respect to which the CMB is roughly uniform, you actually have actually a kinematically induced dipole because LISA, you think of it in the solar system, right? And so you have a dipole, and thanks to this dipole, you end up actually being able to distinguish between, to be able to tell if something is circularly polarized or not. Now, the amount of ability that you have, the sensitivity that you have, is actually studied in this paper by Domke and collaborator, which I actually encourage you to read. But the interesting thing for me is actually this is indeed possible to do with LISA, which is actually great news. Well, and something else I should say just for completeness is that, okay, these models can be studied according to their, well, if you look at the scale dependencies on trivial, you can really say a lot. You can really say, well, we are detecting primordial gravitational waves with PTAs, with LISA. Well, that's not single phase rule. So that's done. You're automatically done. We are detecting chiral primordial gravitational waves. That's not single phase rule. Actually, if you detect chiral primordial gravitational waves, I think that chances are huge that that's related to FFT, the type coupling. That's Chern-Simons type coupling, because it's a very unique signature. It's a rather unique signature of those models. Just for completeness, I should say that you can also characterize not just the 2-point function, but the 3-point function of gravitational waves in these models as well. But since I will have more to say about non-Gaussianity, I'm just going to skip over. I'm going super slow. let me just go straight to the little summary of this part by saying that this class of models, I hope I've convinced you that it's interesting from the top-down perspective. It can be tested in several ways. You just look at the scale dependence of the gravitational wave power spectrum, or you look at the chirality of the spectrum. There's plenty of signatures that can point to these sort of models. All right, now, I want to provide a much broader perspective. In order to do so, I'm going to consider a generic approach to the inflationary particle content. Now, a lot of the ingredients that you've seen are going to come to become useful very soon. But if I'm being very general with you and I just tell you, well, there is an inflationary particle content which is non-trivial, okay? There's not just a scalar field which is inflating for you and nothing else whatsoever. If I tell you, well, there's likely more fields, perhaps the first question you'll ask about those fields is, well, can you tell us more about them? What's their mass? What's their spin, etc.? So is there some observer that has plenty of information about these two key properties? And the answer is actually yes, and so let's get to it. So far, we talked mostly about the power spectrum of something. We talked about gamma gamma, I've talked about zeta zeta. This is just a 2-point function, okay, of these fluctuations. And if we generalize, we've got a 3-point function. It's as simple as that. Now, in cosmology, people call a 3-point function non-Gaussianities. That's what it is. You see a zeta 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 here. B in this equation, in the second equation, is called the bispectrum. And the fact that you've got momentum conservation allows you to draw this little triangle here that needs to close itself for the momentum to be conserved. Now, depending on the configuration of this triangle, if it's, one angle is very tiny or the angle is very large, etc., you get to talk about different templates. What that roughly means is that the momenta dependence of the bispectrum is different. And depending on where this bispectrum peaks, you talk about equilateral shape, local shape, etc., that you might have heard other people talk about. And just to finish this little introduction, the ratio between the bispectrum and the power spectrum square is there because it's dimensionless and because it gives you an idea of the amplitude of the 3-point function. This is a nonlinear parameter, well, because we are considering a 3-point function, and so it's called FNL. And there are very stringent bounds, for example, on FNL scala, which are coming from Planck, etc. But these are roughly the ingredients that we're going to need for this discussion. And one extra ingredient is the following. People like to talk about, for example, in single phase roll inflation, so this is the simplest thing, you will always hear about these consistency relations. What are they and why are they useful? And why are they important in the context of actually observables for multi-field inflation? Well, let me remind you about that. If we consider, let's say, the scalar 3-point function in a specific limit, which is known as the squeeze limit or the soft limit, we have a specific relation between the squeeze 3-point function and the 2-point function. Now, those among you familiar with word identities, this is actually essentially a word identity, but let's not get into it. But there is a very specific relation. Madasena pointed it out. The fact that it exists is related to a residual gauge diff in the inflationary Lagrange. Let's just take it as a fact that it exists. Why do I care? Well, I care because if we are investigating the 3-point function of inflationary correlators, trying to get any information, any physical information about the particle content, we must be wary of the fact that some of this information in the squeeze limit is actually not physical, is actually a gauge artifact. So if you calculate zeta, 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 for example, in the squeeze limit, and I'm looking at the central equation in the slide, we get a standard 1 over k1 cube, k3 cube, that's essentially dimensional analysis. But the physical information here is not in the B0 term, which is the leading one. As it turns out, it's actually in the B2 term, okay? So that's where the physical information is. And this very fact is the one that leads us to say that in single phase roll, B2 is the first physical information that you get. And therefore, this nonlinearity parameter FNL is going to be small, is expected to be small. And if you see an FNL which is larger than that, you can roughly speaking say that, well, you're ruling out single field inflation. So FNL of order 1 or larger is typically considered as a smoking gun for something which is rather different from multi-field inflation or multi-clock inflation. I'm not going to get into the difference between these two, okay? Now, I'm mentioning this because there's plenty that we can study and learn as soon as we consider models with multi-field inflation where the consistency relation no longer holds. Let me get to that. So if we want to learn about the inflationary particle content, as soon as we suspect that there's more to it than just single fields for all, the first place to look is squeezed limit of, for example, in this case, the scalar bispectrum, but the same is true also for the mix and the tensor. But the scalar is just easier to show you, okay? Just consider this formula, we look at it in the squeeze limit. The right-hand side, there is the standard contribution, this is dimensional analysis. But then, as you can see, there is a scaling k1 over k3, which doesn't have an integer power. In fact, it's a function of 3/2 minus nu, and nu is defined below. Nu itself is a function of m, which is the mass of these extra fields that are there during inflation, and s, which is the spin of these extra fields that are there during inflation. So you can see that just by looking at the k scaling of the bispectrum in the squeeze limit, we learn crucial information about the mass of these fields and the spin of these fields. So that's great. That's one way to probe this, a great way to probe the particle content of inflation. And then this PS that you see is actually a Legendre polynomial there of degree s. That means that you also, if you have spinning fields, you get an extra angular behavior that you can test for. So I hope in this rather, quick slide that I convinced you that if you want to test the extra content of inflation, you can do all the things that we have talked about so far for axion gauge fields models. But this is much more general than that. This is generic content with a certain spin, with a certain mass, and you can test it by looking at the squeeze bispectrum. And you will see me going rather quickly because I went slowly in the first slide. So forgive me if I don't say everything that you see written down here. Now, one thing I want to stress in this slide is that, okay, zeta, zeta, zeta is something that we can look at. This is the expression that we get. It's very similar to the one we had before, very, very similar. There are just two additional pieces. The first piece is e to the minus pi mu s. Now, the mu s is proportional to the ratio m over h. M is the mass of the extra particle, h is Hubble. And so this is a serious suppression so long as m is over the Hubble or larger. And this makes perfect sense because remember, we are working at the energy Hubble. And if a mass is over the Hubble or even much larger, then we expect to be able to integrate that field out. And so this e to the minus pi mu is actually there as a sanity check on what we're doing. The non-analytical scaling is there as well. And for large masses, you also get this cosine. This cosine is new here. It gives you some periodic feature in the 3-point function. But again, you do get periodic features, so you're excited about that. But don't forget that you get a mass suppression as well with this Boltzmann-like e to the minus pi mu. Okay, so what we learn from this equation in the slide is that if you have spinning fields, again, things are even more interesting because you've got the Legendre polynomial, so you're very excited about it. But if one is aware of the fact that spinning fields, especially spin-2 fields, have rather strong bounds on the mass, on the allowed mass for the fields, that means that you also get a rather strong mass suppression in front of this 3-point function. So one needs to be careful about that. So spinning typically means great signatures, but it also means that the signatures are slightly suppressed because the mass is having an effect. And this actually can be made very, very precise, but I'm not sure I have time for that. So just trust me that, for example, for spin-2 fields, you can have a massless field, which we certainly know you can because that's GR. Remember, a massless spin-2 field, that's what GR is. But if you want to play around with unitary representations, which you need for your theory to make sense, as soon as you have an extra spin-2 during inflation, it can only be either massless or massive, but then there are very important results that tell you that, okay, if you've got GR, you've got one massless spin-2 field. If you've got anything else that's actually spin-2, then it must be massive. And this is a very well-known result that we can talk about. So whenever you want to consider extra spin-2 during inflation, you must consider massive fields. And this comes with its consequences because the mass is rather large. So it's hard to get signatures. Let me skip this actually. But if you're interested, we can talk about this. And as promised, I don't want to talk a lot about this, but since I showed you everything to do with zeta, 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 I don't want you to suspect that, let's say, mixed non-Gaussianities such as gamma, zeta, zeta somehow behave differently. No, they behave exactly in the same way. You recognize the same formula. There is an epsilon 2 in this first formula, but that's essentially, that's trivial. That's the polarization tensor there. So it's exactly the same behavior, gamma, zeta, zeta, the same way as zeta, zeta, zeta. And we just stress that. So also mixed non-Gaussianities are very interesting when it comes to testing inflationary particle content. And for the people that are familiar with this in the audience, I will also tell you that if you've heard about tensor fossils or fossil fields in inflation, and this is the story where you go look for information about non-Gaussianity, not in the 3-point function itself, but in the anisotropies of the 2-point function. This is a long story, but it can be done. When you have long short mode coupling, what your bispectrum does, so you have a squeeze bispectrum, what this squeeze bispectrum is doing is, first of all, giving you a nice, interesting 3-point function. But it also gives you, looking at the second equation in the slide at the bottom, it also gives you an anisotropy in your power spectrum of the short modes. This power spectrum anisotropy, you can think of it as QLM, and QLM knows about non-Gaussianity. You can see here the QLM is proportional to gamma, zeta, zeta, for example. So another way to test non-Gaussianity is actually to look at anisotropies of the 2-point function. And you might not be tempted to do that because you might say, well, if I got the 3-point function, why should I go bother with the 2-point function? That's normally correct. And this is a secondary, I would say second rate observable whenever you can access the bispectrum directly. But if you're trying to test tensor non-Gaussianities, for example, at small scales, well, then we know there, and this is paper by Bartel and collaborators, that the propagation effects. So let me just give you a better example. If you like LISA and you would like to, or any laser interferometer, would like to test non-Gaussianity at those scales, well, you're going to be tempted to go and look for the non-Gaussianity there. As it turns out, because these gravitational waves have had to go through structure all the way, they have to they have their own history and they have to go through structure to get all the way to the detector. As a result of this going through structure, even if they were primordially correlated with each other, even if you had a primordial non-Gaussianity, this non-Gaussianity is actually typically washed away by the fact that you go through structure. Now, the only exception to this is a bispectrum configuration, which is known as ultra squeezed. And the only way to test it is actually to look at anisotropies of the power spectrum. So this is where this observable, which is otherwise second rate, I would say, with respect to the bispectrum directly, becomes first rate because the bispectrum is not available to you. Okay. And let me just, and this story goes on for a while and you can do lots of interesting things with them. But I think I have just a few minutes now, 2-3 minutes. Savas, or do I have?
Yes, 3-4 minutes. Yeah, you have
3-4 minutes. Okay. So this story about non-Gaussianity and tensor fossils goes along. There's much more that you can do with it, but I won't talk about it. I just hope I've convinced you that you can look at the squeeze limit of scalar, tensor, and mixed non-Gaussianities, learn a lot about mass and spin of these extra particles. And if that's not available, you can look at tensor fossils. You can look for the anisotropies, and that will also know indirectly about non-Gaussianities, and therefore about inflationary interactions, therefore about inflationary particle content. Now, let me just recap. What I hope we have learned is that extra fields can be probably a squeeze bispectrum, okay? They break consistency relations, of course. Now, as it happens, it's even more intriguing to look for spinning fields because they have a richer set of signatures. Now, often they come with mass bounds and therefore there is a suppression in the signal. But even in the case of spinning fields, there are ways around this. There are clever ways to have your spinning fields leave their interesting imprints in your cosmological observables. And these are not ad hoc solutions. You can actually have that in a rather natural way. And maybe if I don't get to that, we can talk about it during the questions. Now, one thing that I've not talked about, and there won't be time to talk about, but it's important, is that I've been talking about the mass and the spin of this spectral particle. It also is important to talk about their coupling. Now, if they're all non-minimally coupled, that's the end of the story. But if this spectral field content couples to the inflaton in interesting ways, perhaps directly, so not through gravity, then the phenomenology on the gravitational wave side of things, but also in general, becomes more interesting, because while you can exchange energy between these sectors, these otherwise very massive and very quickly decaying modes can actually live for much longer. And for the expert in the audience, this can also help you with what's known as the Iguchi bound, which is a bound stemming from unitarity constraints on your field content. And again, we could talk about it if you want. And yeah, just to give you an idea, that coupling is important. If you're familiar with quasi-single field inflation, there too, this is the first line here, the first formula, there too, there is of course minimal coupling between the extra scalar field sigma and scalar fluctuation zeta, which in this Lagrangian is written as theta, just to conform with standard notation. We have already talked about direct coupling or the minimal coupling before in the FFT type coupling. Remember this lambda chi FFT that we had in the first part of the talk? Well, that's also on a minimal coupling, and that also gives us very interesting feature. So when we say that we are eager to test inflationary particle content, we should remember that in doing so, and in looking, for example, at non-Gaussianities, we are going to be automatically testing the mass, the spin, but also the coupling of the inflationary particle content. The coupling is just as important, sometimes more. Okay. Now, I don't think there will be time to talk about this. So let me just say that I've been very specific in the first part of the talk, talking about axial gauge field models. I've been very general in the second part of the talk. I haven't told you anything about the specific model that I'm testing. And that is why, well, the reason I did that is because you can test the generic inflationary particle content by using an EFT approach, and there are several ways to do it. There are actually several approaches within the EFT approach, and I can point out to a few, but there are recipes or the cooking instruction as to how you go about it, and you can actually describe the inflationary particle content in full generality through an EFT that also takes into account the fact that your extra fields can be directly coupled with the inflaton. Being directly coupled with the inflaton is actually very intriguing when it comes to signatures. And this is just an example of that. There's no time to get into it. Let me just conclude, actually. Small scale, yeah, plenty of stuff we can talk about. Let me just conclude very quickly with these two slides. The first one is that, well, we have learned that the most dramatic signatures correspond to no minimal coupling of spinning fields to the inflaton. You can do it, you can go at it in different ways. The EFT way is the more general one. I haven't shown you the Lagrangian of the EFT, but you can trust that the EFT does its job. The advantages, the obvious advantages, is that if you have an EFT approach, then essentially by construction, you're going to be able to describe almost all that's possible. Okay, if you want to describe all the possible signatures, if you're a signature-oriented person, well, the EFT is great. You just write it down, all the possible operators compatible with the symmetries of your theory. Everything that can happen will happen in that one Lagrangian. So that's great. But, and this is very specific to the EFT approach that's most popular, you have to remember that the one that's most popular goes under the name of effective field theory for inflation, and it's not a generic name. It's actually a name that means a very specific approach. It's a great approach, but it's an effective field theory of fluctuations around the FW. It's not a full effective field theory. And that means that even if you identify a specific operator in this Lagrangian that gives you a specific signature, you still have a little bit of work ahead of you to assign that specific operator to a full Lagrangian, one that is able to give you an inflationary background and inflationary fluctuations. And this might be a rather technical point, but it is an important point, so I wanted to make it anyway. And just conclude. This is the actual conclusion slide. So I hope I've convinced you during this talk that very soon we're going to cross qualitative threshold when it comes to important observables. R, remember R 10 to the minus 3. It's great for, let's say, Starobinsky model, which does very well from, I think, every point of view. FNL order 1 is also qualitative because, well, FNL 1 or larger, especially in the local configuration, means something is up with something different. Then single phase Laurent inflation is actually taking place, which would be fantastic. So we're going to cross this very soon. So we're going to learn a lot from observations very soon. But in the meantime, there's a lot that we can do on the theory side. We have ways to test the mass of the spin or the inflationary particle content, but we need to focus, at least in my opinion, a little bit more on the couplings. And this is actually happening very recently. People are focused also on the coupling of this content. And to be slightly more on the mathematical side, there are very important implications that come from, for example, unitarity constraints. Now, there is no time to talk about unitarity, but essentially, if you remember for your QFT class, if you want probabilities to be conserved, then that's unitarity for your correlation functions. Right? We talk about correlation functions in inflation, but for your S matrix in general. So if you want your S matrix to be well behaved, then it better be unitary. And these unitarity constraints actually have a lot to say about your inflationary field content, in particular the mass of the inflationary field content, and therefore they have a lot to say also about the signatures of your field content. So they are very consequential as to what you can observe, and it's interesting to study them. And so in general, I guess there's plenty that we can do, and we can take different approaches. And my feel is that we need to combine them. So it is good to be looking at everything that is testable, but in my opinion, there's even too much. I think there's so many things that we can test that we can actually afford to combine the requirement that something is testable with the requirement that is also compelling, let's say, from the model building point of view. And so if we put them together, I guess we've got a great combination of criteria as to what to test and why. And let me just stop here.
Okay, thank you, Matteo, for this very nice talk. So we have a few minutes for comments and questions from the audience. So if anyone wants to ask.
Yeah, participants. Can I see? Yes. Yes.
Well, if nobody asks, let me break the ice. Matteo, thanks for a very nice talk. So, of course, it's not just gravitational waves that you could be after in this kind of Chern-Simons type couplings to the inflaton. You were mentioning a function of the field phi coupled to FF dual. You could then cook up a reaction, a back reaction of the gauge fields onto the scalar curvature and produce a very high peak in the curvature fluctuations, which could then collapse to form primordial black holes at a scale which is directly probed by Lisa also.
Lisa.
No?
So indeed, I skipped the slide, but it was there, and this is the case for the abelian case. So I forgot to say that. Well, I skipped this part, but the SU2 gauge field is one of the possible configurations. And in there, in that specific model, the gravitational waves are a bit of an advantage with respect to, so that the tensor sector is a bit of an advantage with respect to the scalar sector because their gravitational waves are sourced directly and scalars are not. But this is the case only for the SU2. Now, as you point out, intriguingly for the non-abelian case, then the mechanism is the same because while you source the gauge field source gravitational waves and the scalar degrees of freedom in the same way, so everything that's intriguing on one side, perhaps even more, is intriguing on the other side. And indeed, as you say, and you know, a lot of people have also been looking at, for example, primordial black holes or in general bump in the scalar spectrum coming from this model. Yes. indeed.
So that would be a complementary probe, because you would look for a chiral spectrum and then look also for the counteraction of that curvature fluctuation on the production of black holes.
Yes.
So it makes sense to have a multiple approach, multiple probe approach.
Yes, and I mean, in fact, for this gauge field models, what I wanted to stress is that even if for some reason you decide to play just with one hand, right, which is a gravitational waves hand, and not use everything that you can, you still end up with plenty of tests. And so, of course, if you decide to play all your cards as you should, then you end up with possibly even more ways to rule it out. Yes.
Okay.
Okay.
Yeah. Sorry.
Yeah. Any more questions?
Well, if nobody asks, can I ask you about the sensitivity of LISA to these spectral features? Do you think you mentioned the ability, this is what we did with Ballerino,
yes.
how LISA's rotation around the sun allows you to, in its response function, to be able to distinguish chiral stochastic gravitational backgrounds. Now, of course, it is important that you are above the sensitivity threshold of LISA, and this requires some fine-tuning in the parameters so that indeed it's above sensitivity.
Yes.
So could you comment on that?
Yes, I can comment on that. In fact, this is so one thing which, at least initially, used to bug me about this model. This is something I thought about quite a lot. Let's see if I can just go back to the Lagrangian. Yeah. So let me just repeat for everybody that this lambda here, right? It's a whole point. For lambda being very small, well, this FFT that doesn't play a big role, you don't get the current signal, and so okay, things are not as interesting as they used to be. The source contribution is smaller than the vacuum fluctuations, and so less interesting. Now, for lambda to give you something that you want, lambda needs to be of order 50 or 100. Now, if you hear 50 or 100, you don't like it, okay? Because, well, we're pushing it, really pushing it. But it's not that perturbative expansion still works. This can be proven, but it sounds like it's quite large. Now, one paper that was written down by Dalagatam, who has considered a supergravity embedding of this Chromo natural inflation, and even this very model that I'm writing down here. So in that paper, if I remember well, but this is, I think this paper is 1 year old, so it's not very old. What he found is that, yes, indeed, lambda, just saying it's 50 might look a bit of a fine tuning, but he has found a dynamical way to get lambda to be of order 100, actually. And this lambda of order 100 would give you enough of a boost to get primordial gravitational waves at those scales. So I guess the biggest worry for me was this lambda order 100, but there is a dynamical way to get it, which is much less of a tuning than just saying, okay, I give you this lambda, play with it. So it makes me feel a little bit more comfortable about this. Now remember though, that because of the back reaction, at least in the SU2 case, the other limit, it's not a limitation, but it's a stuff to be aware of. The source contribution in this model can indeed be larger than the vacuum fluctuations, but they cannot be one full order of magnitude larger. So again, that doesn't mean anything. You can still get LISA, you can still get the signal to be chiral, etc. But the chirality would not be one, right? Because you cannot be incredibly larger than the vacuum fluctuation. It might be 0.8, 0.9. But it cannot be fully one, as if the vacuum doesn't exist because it's 3 orders of magnitude smaller. But other than this limitation, I don't see other ones. And so you should be able to do that, yes. Now, the things that you can ask, and I don't know the answer to, is the cross correlations of different interferometers on the ground. So I know that Rob Caldwell has worked on this, but I don't have a number of to what signal do you need in order to be able to tell if the chirality is there. I don't know the sensitivity that comes out of cross-correlating different interferometers. I know it's possible in principle, it has been shown, but I don't have the numbers ready there.
Thanks.
Okay, so there was a comment in the chat. If you can put the paper, the reference to the paper you just mentioned in the chat.
Oh yeah. Of course. In fact, you know what? I can do it right
Okay, so
away.
in the meantime, do we have any more questions, comments?
Okay.
Okay. Okay, so this is the paper. Thanks.
I think well, no, it's a figure about. I figured out where it is. I don't think it's.
Yeah.
Yeah.
Okay. So, okay, so if there are no more questions or comments, then we can thank Matteo again for this very nice talk. Thank you, Matteo.
Thank you.
Yeah. They can stop the recording.